Detailed note on electromagnetism. Electromagnetism is a fundamental branch of physics that studies the interactions between electric fields and magnetic fields. These two forces were once thought to be separate, but were unified in the 19th century by the work of scientists such as James Clerk Maxwell. Electromagnetism is one of the four fundamental forces of nature, alongside gravity, the strong nuclear force, and the weak nuclear force. It governs a wide range of phenomena, from the behavior of everyday electrical devices to the propagation of light and other electromagnetic waves. Key concepts of electromagnetism, electricity and electric fields. 1. Electric charge, the source of electric fields. 1. There are two types of electric charges, positive and negative. 1. Like charges repel each other, and opposite charges attract. 2. Coulomb's law. This law describes the force between two-point charges. 2. The magnitude of the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. F equals K dot operator Q1 Q2 R2 F equals K underscore E, C dot, frac, Q underscore 1 Q underscore 2, R squared, where FF is the force between the charges, K underscore E is Coulomb's constant, Q1 Q underscore 1 and Q2 Q underscore 2 are the magnitudes of the charges, and RR is the distance between the charges. 3. Electric field, E, a field around a charged particle that exerts a force on other charged particles. 3. It is defined as the force per unit charge. E equals FQ. E equals, frac, FQ. The direction of the electric field is away from positive charges and toward negative charges. Magnetism and magnetic fields. 1. Magnetic field, B, a field produced by moving electric charges, currents, or by intrinsic magnetic properties of materials like magnets. 1. It exerts forces on other moving charges, currents, or magnetic materials. 2. Lorentz force, the force exerted on a charged particle due to both electric and magnetic fields. 2. It is given by F equals Q, E plus V times B, vec, F equals Q, vec, E, plus, vec, V, times, vec, B, where F, vec, F, is the force on the particle, QQ is the charge, E, vec, E, is the electric field, V, vec, V, is the velocity of the particle, and B, vec, B, is the magnetic field. Maxwell's equations. James Clerk Maxwell formulated four equations that describe how electric and magnetic fields interact. These equations are the cornerstone of classical electromagnetism, optics, and electric circuits. They are: Gauss's law for electricity describes how electric charges produce electric fields. 1. Nabla dot operator E equals Re0, Nabla, C dot, vec, E, equals, frac, rho, epsilon underscore 0, where rho is the charge density and E0, epsilon underscore 0 is the permittivity of free space. Gauss's law for magnetism states that there are no magnetic charges, and the magnetic field lines always form loops. 1. Nabla dot operator B equals O, Nabla, C dot, vec, B, equals 0. Faraday's law of induction describes how a time-varying magnetic field creates an electric field. 1 times E equals minus partial differential B partial differential T, Nabla, times, vec, E, equals, frac, partial, vec, B, partial T. Ampere's law, with Maxwell's correction, describes how electric currents and changing electric fields produce magnetic fields. 1 times B equals mu0 J plus mu0 E0 partial differential T, Nabla, times, vec, B, equals mu underscore 0, vec, J, plus, mu underscore 0, epsilon underscore 0, frac, partial, vec, E, partial T, where mu0, mu underscore 0 is the permeability of free space and J, vec, J, is the current density. Electromagnetic waves. 1. Wave propagation. Maxwell's equations predict that electric and magnetic fields can propagate through space as waves. 1. These waves travel at the speed of light, c equals 3 times 108 meters, sc equals 3 times 10 to the power of 8, text, meter per second. 2. Electromagnetic spectrum. Electromagnetic waves cover a wide range of frequencies and wavelengths, including radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. 3. Properties of electromagnetic waves. They consist of oscillating electric and magnetic fields that are perpendicular to each other and to the direction of wave propagation. They do not require a medium to propagate and can travel through a vacuum. Electromagnetic induction. 1. Faraday's law of induction and Lenz's law describe how a changing magnetic field can induce an electric current. 1. This principle is the basis for the operation of electric generators and transformers. Faraday's law, the induced electromotive force, EMF, in a closed loop is equal to the rate of change of the magnetic flux through the loop. E equals minus d phi b dt, math call, E equals frac d phi underscore b dt, where E, math call, E, is the induced EMF, and phi b phi underscore b is the magnetic flux. Lenz's law states that the direction of the induced current will oppose the change in the magnetic flux that caused it. Applications of electromagnetism. Electromagnetic principles are central to many modern technologies, including 1. Electric circuits, the flow of current through resistors, capacitors, and inductors. 2. Motors and generators, conversion between mechanical energy and electrical energy. 3. Telecommunications, radio, television, and mobile phone signals are carried by electromagnetic waves. 4. Electromagnetic radiation. Light, X-rays, and other forms of radiation are electromagnetic waves that transmit energy across space. 5. Medical applications. MRI, magnetic resonance imaging, radiation therapy, and other diagnostic tools rely on electromagnetism. 6. Power transmission. Electromagnetic principles are used in power generation, transmission, and distribution. Conclusion. Electromagnetism plays a crucial role in both everyday life and advanced scientific applications. From the flow of electric current in a circuit to the behavior of light and the interaction of charged particles, understanding electromagnetism is essential for understanding the natural world and for the development of technology. Maxwell's equations provide the foundation for much of this understanding, while electromagnetic waves serve as the backbone for communications and energy transfer in the modern world.